Hello everyone and welcome to another Flux tutorial. My name is Zach Peterson and today we're going to be working on our Arduino Mega shield board that we started in a previous video. Make sure to check the link in the description for that earlier video. In this video we're going to wrap up the schematics. We're going to show what connections we need in the schematics to use the sensors that we selected in the previous video. One of these sensors does have to hook up to the ADC, and so we'll show how to actually use the ADC to get the most accurate measurements with these sensors, as well as to ensure low noise on the power rail. Make sure to hop into Flux, follow along, and let's get started. So I'm inside the schematics where we last left off. We have our main component here, which is all of our connections back to the Arduino Mega. And then here we have our temperature sensor that we're going to be using as an analog component. And you can see here it connects to one of the pins on the ADC. And then here we have our gas and humidity sensor. This sensor has an SPI interface on it, which you can tell just by looking at the pin names. However, if you look in the datasheet, you'll see that you could also run this as an I2C interface. So I'll get into that in a moment. The next thing that we need to do is, just in looking at this supply, we actually need to do some decoupling between the digital input, so the 3v3 right here, and then the analog reference. Now there's a reason we need to do that. It is because, of course, we want to make sure that we have the cleanest possible reference here. And the reason we want to do that is to ensure that we have low noise when we're collecting this temperature signal with this ADC. So first, let's go ahead and get into the BME 680, and we'll jump into the data sheet. So here's the data sheet for the BME 680. And if I scroll down here, I can actually do a quick search for a couple of important points here. So as we discussed last time, our supply voltage can be basically anything from 1.2 to 3.6 on the I/O voltage. I'm going to go with 3v3. And then here with this main supply voltage, we basically need either 1v8 or 3v3. So we're just going to go with 3v3 to keep it simple. The other thing that I want to look at here is what to do with the CSB pin. Now the CSB pin is actually very important, because if you read this line right here, you'll see that the CSB pin is selecting the interface. So it's based entirely on how you toggle this pin. Now I could use this to connect to an I2C interface, and to do that I would just connect CSB to VDDIO, or I could just pull it down and that will set it to SPI mode. So for this I'm going to use SPI mode. The reason for that is I don't want to go through the exercise of calculating the bus capacitance here for this I2C interface just to ensure that I hit setup and hold times. Instead I'm going to go with the SPI interface, and it's much easier to work with. Now the SPI interface is a little bit faster, so when we use that SPI interface we just need to check to make sure that we don't have to actually use any series resistors on the output from this component. So to check the series resistors, we need to know, of course, setup and hold times, and that is going to be an indication of what the rise time is for these signals. So if you're familiar with digital signals, you will know that, of course, they have a rise time, which defines how fast they transition between different states. And typically, if the setup and hold time is longer, the rise time could also be longer. So just from looking at this timing diagram and then some of the timing diagrams here on later pages, I know that this SPI interface is probably operating on the order of 10 nanoseconds or longer. They don't actually list the rise time in here, but the reason I'm bringing up the rise time is because sometimes you need to put series resistors on the output of this component. So that would be on SDO and then SCK. And the reason you would want to do that is to slow down the edge rate a little bit. That's going to reduce the amount of noise that is being radiated from this device. So for us, we don't really need to do that. We can just use SDO and then SCK as is, and then we'll just make the net connections here to ground that we need to set CSB low, and that's going to enable our our SPI interface. And then here we'll copy this over to this side. We'll set this one to ground. And then the last thing we'll need to do is just set VDDIO and then VDD. So as I mentioned earlier, we're just going to use the 3v3 connection. And we'll drag it down here. And sometimes you can just rotate it. It's going to be a lot easier to make that connection, but we'll just rotate it over and put it here. And then I'll copy it down here as well. So next, we'll want to make these connections back to the microcontroller. So we have to do that through certain pins, of course, on this pinout. So which pins do we need? Well, for that, we need to actually look at an image of the pinout. Now, sometimes these pinout images, they don't necessarily list every function on these pins. Now, this particular one does, and if you zoom in here, it's a little bit hard to see, but down here at the bottom of my screen, you can see what the different pin names are for the SPI interface, and we have them right here. So we have master in, slave out, master out, slave in, and then our chip select, and then our clock. So we'll hook up the clock to 52, and then we'll hook up the MISO and MOSI. So MISO and MOSI are used interchangeably with SDO and SDI. So here, the SDO and SDI pins, we would just hook those up down here in this lower portion of the schematics. So hold on just a moment and I'll go ahead and do that. So we've got our interfaces hooked up. This component is basically ready to go. One thing that you would actually want to do is you would want to make sure that you put some capacitors here from this supply pin to ground and keep them, of course, very close to this IC. Same thing here with this VDDIO pin. So we can just search for a capacitor. We'll actually just use a generic capacitor here. And with the generic capacitors, it's actually really easy to just place a couple of caps that you're going to need for this particular chip. And here we can just connect them both to 3v3. They're both going to be used for the same component. If we want to, we could even put a little comment or note in the layout, or I'm sorry, in the schematics, so that it's very clear where we need to put these particular capacitors. And then of course complete this with ground, and this is going to be good. So here again, we're using the same voltage rail for our IO supply and for the VDD supply, and then that voltage rail is getting decoupled with these two capacitors. Now when you're using these capacitors for decoupling, what you want to do is make sure you select the right case size. Here, this case size that we want to use is actually going to get smaller than 0603. We would want to go down to 0402. So that's what we're going to use. So now that we've changed that for these two capacitors, these are ready to use. So we can worry about selecting an actual manufacturer part number later. The reason for that is, again, these are just generic components. Now, we also need to set the capacitance. And so typically what you're going to do is you're going to use these as bypass capacitors. So you would want to set maybe about 10 nanofarads. So 10 nanofarads is going to be just fine. And we're going to do the same thing for this other one. Okay, so that's going to decouple both of the pins. That's going to be plenty of capacitance that you need to then ensure that you can supply power for those fast edge rates for this SPI interface. Now, if this SPI interface were running faster, we would actually want to use multiple capacitors, and they would need to have smaller values here in order to supply power for these IOs. So next, we want to make sure that we decouple the 3v3 rail on the analog input from the 3v3 rail that's supplying all of the digital stuff. And the 3v3 rail here can be very easily decoupled, essentially by just putting a low-pass filter between these. Now, I could draw it out here like this. Of course, it gets a little messy, and so I think it's a lot easier to just basically draw it out over here in this area. So the way this is going to work is we would basically want to separate these two with some resistance, and then we'll use a capacitor to ground. So we're basically using an RC low pass filter. So this RC low pass filter, we can just grab C1, bring this guy over here. Now with this RC filter that we're going to put here with this capacitor, we would generally want to cut at lower frequencies than we would want to cut when we're using it on an I/O supply. So we're going to increase this capacitance here. And then the resistance that we need for decoupling these two supply pins is actually not a lot. I think everyone's maybe their instinct is to use a very large resistor, but that's not actually what we need to do. We actually just need to use something like on the order of 50 or 100 ohms. Some analog to digital converters will actually supply that value in their data sheet. Here, since this ADC is built into the microcontroller, this input is going to be a high impedance input, and so it's not going to draw a lot of current. So this resistor that we're going to place right here is actually going to have the function of just limiting the current just a little bit, and it's going to then of course set the cutoff frequency or the knee frequency for this filtering action for this RC filter. So here again, I'm just going to draw it in, and then I'm going to just use this generic with 50 ohms, and we're going to select an appropriate case size. Again, let's just go with 0402 to keep it simple. You could go with a larger case size if you were planning to assemble this yourself, but for us, we'll just keep it 0402. Next, the I/O reference voltage. So the I/O reference voltage is important because here we're using a 3v3 I/O reference voltage on this sensor. So the SPI interface is going to be operating at a signal level of 3v3. So we want to do the same with this pin here. So we would want to set this to 3v3. So we're going to set that. And I believe that covers everything. So technically right now in this moment, we would be ready to start laying this thing out. We could get started. I want to do one more thing though, which is to actually apply some filtering here on this line where we are measuring the temperature. So the temperature here is being output from this pin here. And this pin will have some voltage range to it. And if you just take a look here in this data sheet from Texas Instruments, just taking a look here at the voltage, you can get a sense what the output voltage is as the temperature scales. Okay, so we also need a bypass capacitor here for this component. So we're going to add in the bypass capacitor as well. But you can see what the voltage here is. Voltage here is just going to scale from basically 0 to 3v3. So when we set that analog reference to 3v3, we'll be able to measure all the way down to negative 50 Celsius accurately. So with this, what we can do is, since we're measuring a DC voltage, we want to just put a pretty hard low pass filter on this signal line. So we could essentially just copy this and go ahead and bring it over here, and then we can copy this resistor as well, bring it over here. So now we've got our components here, and we can basically just drag these connections, and we now have our low pass filter. Now this is using a technique that is sometimes called charge compensation. There's a guy I worked with on a project, he called it charge compensation. Essentially what you're doing with this filter is you're cutting off everything that's above some frequency, but you don't want to apply too large of a resistance here, because if the resistance gets too large, then this analog to digital converter is going to misread what's being output from this sensor. So generally you don't go above maybe a few hundred ohms on these filters, or on these resistors for these filters. I've typically do this with something more like 22 ohms. So that's what I've done here. So I've set it to 22 ohms. And then this capacitor here is then going to be used to set the knee frequency, or the cutoff frequency, for this filter. So at 1 microfarad, it's actually a little low. We could actually go up to something more like 10 microfarads. And then finally, as I mentioned, we want to ensure that we apply some decoupling here between the 5-volt rail and everything else that is going to appear on this board. So this 5-volt rail, we'll just make this connection here, and we can delete some of these extra wires here. But then we also want to ensure that we apply a bypass capacitor that can ensure that we have stable power being delivered to this component. So because this component isn't operating with a digital interface, what we can do is we can just copy this capacitor and bring it over here. And this capacitor is going to be large enough that it will be able to ensure stable power for this component. So we'll just go ahead and make these connections, and of course we'll bring it back to ground. Can clean these connections up just a little bit. So now that's all cleaned up, and I think we've covered everything as far as these additional components and then some of these issues with the supply. Now, of course, we could access some other features on this microcontroller if we want. And one of them that I want to point out is there is actually a JTAG interface. So if we go over here and we take a look at this pinout image, you can actually see here that we have all of the 4 main signals that you would need to implement a JTAG interface through these analog inputs. So this is one instance where I don't think I've seen a microcontroller that actually implements a JTAG interface through its analog interface, but this microcontroller does, and it's these pins right here. And so if we go back into the schematic, that would be these 4 pins right here where my mouse is. So we could add a JTAG connector. So if you go here to the library and just search for JTAG and then select items with footprints, you'll actually see here we can have a 10-pin JTAG header if we want, and we could add this into our design. So we're not going to do that here. We're not so worried about JTAG at the moment. And of course, you can just access the pins directly coming off of the pin header on your shield board. But we have everything that we need now to start going through the layout. And so we're going to get started on that here right now. So when I'm in the PCB, you can see it takes just a second to load. But once it does, we just need to do a little bit of repositioning for our shield board, and we're basically good to go. Now, you know, these components that appear on this board are actually really small. And that's one of the things that is, I think, kind of fun about working with an Arduino Mega shield board is, you know, these boards are mega sized. So you got a lot of room to go through the layout and place things where you want. Whereas if you were using something like on an Arduino Nano or maybe an Arduino Uno, you're not going to have as much room. So what I'm going to do now is go through the layout, and I'm going to go through and show where we need to place everything so that we have low noise between this component that has its digital interface and then this component with its analog interface. So here's what my finished layout looks like, and you can see here just how small these components are in comparison to an Arduino Mega shield. Here we have the gas sensor connected to the SPI interface, and then over here we have our temperature sensor going over to the analog interface, and then here we just have some decoupling on the AREF pin. Now you've got plenty of room on this board to start adding more stuff, and what I'm going to do is I'm going to actually publish this to the public library, and I'm going to let all of you folks out there who are watching this play with this board on your own. It still has some cleanup that needs to be done. You can actually see some DRCs down here that need to be fixed. That's okay, we'll get to that, but this is basically what it looks like. So I've done this because, of course, the digital interface is down here, and the best way to prevent this digital interface from inducing crosstalk into the analog interface is, of course, to keep it separate by as large of a distance as possible. Here with this analog interface, it doesn't have any digital stuff running near it, so it's not going to be susceptible to any digital crosstalk. And then of course we have the ground on the back side of the board that is also going to help prevent crosstalk. You can also see here I've used some fat rails to try and route power to all of our different components, and that provides a nice easy way to ensure everything is connected. If you want, you can add more components to this, redo the routing on the back layer, or of course you could change one of the rules for the layout to then add more layers into this board. So here I've set this to a standard 2 layer. You could of course set this to 4, 6, 8, whatever you want. Thanks everyone for watching this tutorial. Make sure to check out the links in the description and make sure to hit that subscribe button. You'll be able to keep up to date with all of our tutorials as they come out. We'll see you next time.